Hello everyone, welcome to this week's Crunch seminar. Today we have one talk by Nilo Schwencke, who will present his work on the kernelization of natural gradient methods for physics-informed neural networks. Nilo graduated from the École Polytechnique in France with a major in computer science. He then completed a master's degree in mathematics at the Karlsruhe Institute of Technology in Germany. He's currently finishing his PhD in scientific machine learning at the Paris-Saclay University. And with a short introduction, I invite you to present your work, Nilo.
Thank you, Vivek. Hello, everyone. So today I will present some works I did during my PhDs about the link between natural gradients and kernel methods with application to physics-informed neural networks. So to give a brief reminder, so what is a physics-informed neural network? It starts from the following problem. We have a PDE, that is an operator D, with some given boundary conditions, and we want to solve this equation. So the PIML key idea, as introduced by Racy et al., is to define this loss and to minimize it by the usual optimizer we use in machine learning, so ADAM or LBFTS. And the problem that we have with this when we do this is that we have the performance compared to traditional solvers is not very good. So for instance, we have here on the Laplace equation in 2D, after 10,000 iteration, we reach an L2 error that is of the magnitude of 10 minus 2. So to understand this, we will take two ideas, or we will illustrate this on two ideas. So first, the intuition from NTK. So we will see it in more details later, but the idea is that the NTK compute or dictates what is the impact of changing the value at the red dot here on the other points of the domain. And we see that when we do the traditional gradient descent for pins, in fact, the signal is not localized around the point. So it means that when we change the value at here, so here, for instance, or here, in fact, we are changing the value of the function here. So of course, this is not what we want. We would like that when we change the value here, then it has an impact that is localized around the sample point. So this is the first idea. The second idea is so some intuition from Fourier. So you define the partial Fourier series. This is an object that is completely well conditioned, because if you take the SVD of the Fourier partial series, you get all the singular values equal to 1. But now, if we look at the SVD of the partial Fourier series through Laplacian, then you have that the spectrum is this one, so 4p squared k squared, and in particular, it's something that is not well conditioned, because you can have many orders of magnitude between each singular value. Okay, so one of the ideas to remediate this problem is a natural gradient. Okay, so what is natural gradient? So first we will investigate it in just a simple L2 regression context, and we will see later how to extend it to pins. So you have the classical MSE loss of neural networks, and if in the limits where you have an infinite number of samples, then you recover this L2 loss, which is simply the integral of the square between u and the target f. And the good byproduct of that is that we can define a Fréchet derivative of this functional loss. And we have a functional gradient here. And now we can define a gradient descent in the functional space by this equation. And we see with simple calculations that this has an explicit solution, which is given by this formula. And so how do we interpret that? Is okay, on the picture here. So we are here, we want to go there. And this formula tells us that we go in a straight line with exponentially fast convergence to the target f. Okay, so it means that we are here and we will go very fast, and then arriving near the target, we will go a bit slower, but we will be already very close to the wanted target. Okay, so now how can we apply this to neural networks? The problem is that we are not free to move in the whole space. We are constrained by the architecture of our neural network. So we can modelize this as a manifold given by this formula, okay, and which is parameterized by the parameters of the neural network. And locally, so at a given point theta, we can approximate the manifold by a linear space, which is the tangent space to the manifold. And in the functional sense, this is the set of the admissible directions we can take to move on our manifold. And so the idea of natural gradients is really to say, okay, we want to go in this direction. This is not possible. So the best we can do is to project this direction into the set of possible directions, which is the tangent space. Okay. And once we did that, we just have to retranslate it back into a parameter update. And this is done through this pseudo inverse of the differential of the neural network. Okay. Okay, so now we will connect it to the theory of reproducing kernel Hilbert spaces. So very briefly, what is an RKHS? An RKHS is just a Hilbert space in which the evaluation is continuous, or equivalently is a space where you have a kernel K, and you can approximate any function as a finite sum of those kernels. Okay, it's a bit abstract, but it's a theory that is very well known and used, especially in statistics. And we have some facts. So any finite dimensional space is an RKHS. And something that is very important to us is that so on a finite dimensional space, we can write explicitly the kernel using the GRAM, the pseudo inverse of the GRAM matrix, which is the matrix defined by the inner products between the functions, so the basis of the space. And the main fact is that the projection into a space that is an RKHS is defined through this formula. So in fact, here we compute the projection, and so what this proposition states is that this projection is simply given by taking the scalar product between the kernel of H0 and the function f. And the link is, okay, if we take H0 to be the tangent space we defined before here, we can define through this proposition this projection that we use here. Okay, and so concretely using this proposition, we define a new object that is called the Natural Neural Tangent Kernel. Okay, which is a generalization of the natural tangent kernel introduced by Jacot et al. Where in their case it's just the identity here, but in our case we replace the identity by the gram matrix of the partial derivatives of the neural network. Okay, and so using that we recover the traditional update of natural gradients updates. Okay, using the pseudo inverse of the gram matrix. Okay, so now the problem is that it is well known that this update is intractable in practice because computing G is at least quadratic in the number of parameters, and inverting it is cubic. So if you have a neural network that has a few hundred parameters, it's still doable. But if you take millions of parameters, there is no chance to compute it. And so here we introduce a new idea, is that, okay, if we take a look at the functional dynamic, this is something that is already exposed in the seminal work, I mean the paper that introduced the NTK, that in the functional space, we can write the dynamic through this equation. Okay, so what is the intuition behind? Is that here, this is the gradient path of our neural network. And we want to know what will be the impact of changing the function with respect to the points of the dataset xi. And so we know that the difference that we will retropropagate is given by the difference between the target yi and the value of the neural network at xi. And we have this, so the NTK or NNTK in the case of natural gradient, that measures what is the influence of xi over x. And so in the end, the average impact on x or the total impact on x will be the average of the impact of the modification at xi. So we reweighted by the influence of xi on x. Okay, so this is the intuitive idea, but from the mathematical point of view, what we can say is that, okay, we can be more precise than what we said before, that is that the update happens in this green space here, which is a tangent space, by defining a new space, which is what we call the empirical tangent space, which is given by the samples we use to optimize. I mean to define the residue. Okay, and so now the idea is, okay, we have a new functional space defined by the NTK or NTK, but then instead of projecting into the tangent space, we can project into the empirical tangent space. Okay, and when we do that, the pleasant result is that there is some algebraic simplifications that appears, and we can rewrite it like this. So by this formula here, where phi hat is the empirical Jacobian, and nabla L hat is simply the gradient, the functional gradient evaluated at the points of the dataset. And so the key fact is that computing this update becomes linear in the number of parameters when we use a batch that is, let's say, reasonable, so a few hundreds. Okay. And okay, we have also we have some properties in the paper that show, okay, so under some assumptions, this update can be exact. And another interesting byproduct is that it gives us an optimal criterion for the choice of the collocation points here. Okay.
Can you say, Nilo, can you say exactly what is P and S? I see the definition, but maybe so S is the total number of points that you're sampling, right?
Yes, yeah, sorry. P is the number of parameters and S is the number of samples.
So
yes,
P
sorry.
P is the number of parameters of the network.
Yes.
Okay, but that will be, okay, but you're taking the minimum of the two. Okay, the
Yes.
complexity is the minimum of the, okay, I got it.
Yeah. Okay, so how can we apply it to pins? Well, the idea is that we just check the two losses here, so the regression, so the traditional MSE and the pins loss, and we see that essentially the only difference is that in this loss the terms D and B appears. Okay, so one way to extend our previous work is just to say, okay, in fact, the pins are essentially an L2 regression problem. It's just that instead of regressing with our neural networks directly, we regress with what we call the compound model, which is this whole model here, where we start from a parameter theta. Okay, first we have some neural network, but after applying the PD and the boundary conditions, we get a function that is in, okay, L2 on omega and L2 on the boundary, but this is essentially just another L2 space with respect to omega times d omega. And so we can reuse all the framework we developed before, but on this compound model. Okay, so what is the mathematical idea behind is that there is the target here, so F is the source and J is the so the boundary conditions, and if D is not linear, so in fact we can define also tangent space of the manifold defined by the operator, and so we can first project on this tangent space, and then the neural network can be, so we represent it by this line. So it is a subspace in the space H of solution. And so we reproject into the image of this approximation space. And this is the natural gradient of pins. Okay, so now how does it work in practice? So we tested it on on a benchmark of not some equations. So on the 2D Laplace, so we see that compared to ADAM or LBFGS, we have a few orders of magnitude. I mean, the solution is a few orders of magnitude lower, comparable to energy natural gradient by Marius Zeinhofer and Johannes Müller. And so, okay, it's the same on heat. On Laplace, 5D Laplace is comparable, and on Galerkin, it was performing better. The difference being that in this case, in fact, we can show that the NGD and AnaGRAM are essentially equivalent on linear problems, but this is not true for nonlinear problems, and in this case, we perform a bit better. Okay, so this is the first paper we published, and no, but yeah. So sorry, before that, the interpretation in terms of NTK. So you remember? So I showed you the NTKs at the beginning, and we see that is the same thing. Is so the impact is when we take the traditional gradient, the impact is not localized around the point. But now, if we take the NNTK, you see that it is much more localized around the point, which is of course suitable. And so this is at the beginning, and at the end, this becomes so even better, because here we see that is strongly localized around the points, and we can interpret that by saying that the problems becomes somehow separable, in the sense that when we modify the value at a point here, the influence it has on another point of the dataset is very low, and so we can change the values at each point independently from the others. And this has a connection with the green function framework, and this is what we will see at the end of the presentation. Okay. So before that, so this was the first contribution, so the AnaGRAM paper, and we did some more work.
Nilo,
And
can you go back and show us again how you compute the NNTK? Because
the NNTK.
Yeah, how
yeah,
you actually compute the computation of that? I saw it somewhere in the okay. So
so no, it's before. Yeah, it's this one. Yeah.
right. So the first term is the derivative. So that's what you call phi later. That's the differentiation with respect to the parameters of the network, right?
Yes, exactly.
And that's you do with auto differentiation.
Yes. Yes.
And then the Gramian. So this is the inverse of the inner product of those derivatives. So the inverse, you do it with the trick that you show that, and the cost is the minimum of the PS square P square S, right? That's
exactly.
Okay, that's how the computers, and that, but that is computed continuously, right? In time dependent, every iteration.
Yes, at every iteration. Yes.
Okay. And
yes.
And the cost is not. I mean, it's fine. I think. Can you go back to one of the plots where you have real time, not a number of iterations?
Yeah, this is a running time.
The running time, yeah. Oh, yeah. So you can see that then all the curves bunching up when you do the. Oh, okay, no, okay. You still maintain the advantage, yeah.
Yeah. I mean, we do less iterations, so each iteration is more costly in terms of time, but overall, because we need far less iterations, it's still competitive.
Yes, exactly. But why you said for the linear case, the NTK and no, sorry, the energy natural gradient and the
Yes.
AnaGRAM are the same, but not for Laplace. Looks it's okay for the same for his, but
No,
not for
okay.
Laplace.
In fact, the difference comes from something else, which is the regularization, and this is what I focus on the remaining of the talk.
Fine. Yeah. Okay. Then it's a good point to move to your second part. Thank you.
Welcome. Okay. So precisely so in practice, so I defined the pseudo inverse of the Jacobian, but in practice we need a regularization scheme, otherwise it doesn't work. And so the way we do it is applying a cutoff. Okay, so what does it mean is we define a level alpha, and we look at our singular values, and all the singular values that are greater than alpha, we just take the inverse, and for the other singular values, we just drop them. Okay, so in the end, our update is computed through this formula. Okay, well, of course, it's done in a matrix multiplication way, but mathematically, it's equivalent to that. Okay, so with a rank that is defined by the cutoff level. Okay, this here. And now the key is to define this quantity that we call the reconstruction error that measures, how far or how much signal you lose when you take this so partially reconstructed gradient with respect to the full gradient. Okay, and so the intuition behind in the limit of infinite number of samples is that we have our tangent space in green here. The SVD gives us the most important directions in the tangent space. And when we apply the cutoff, we just keep those R alpha most important directions. And the RCE measures the orthogonal part of the signal, which means that, okay, all so the orthogonal projection of the nabla L into the space that is orthogonal to the R alpha most important component. So in this case, it will be essentially this vector here. Okay, and the other key intuition is that RC of 0, it means that here n is 0, so this part is discarded, and so it's just the norm of nabla, which is the same as the loss. Okay, so now having this in mind, so the singular values in orange and the RC in blue, we look at those curves. Okay, so this is a run of AnaGRAM on the heat equation, and we plot the two curves, so the singular values and the RC. And in red is the cutoff. So here it's at 10 minus 3. Okay, so it gives us a number of components that are kept. And here in green is the train loss. And what we see is that, okay, we start, so iteration 0, that's the beginning. After 40 iterations, this moves a bit. And after some point, we have that the crossing between the two curves goes beyond the number of components that are kept. Okay, and what we see, okay, it's not very clear here, but is that here it becomes begins to become flat. Okay, and what we observe is that in fact this is a general phenomenon. Is that when we continue the algorithm, then we have that the RC begins to become more and more flat. Okay, and at the end of the optimization, it is completely flat. Okay, and this gives also an explanation to what we saw. So here, for instance, or here, which at first sight seemed very bizarre, is that when we look at AnaGRAM or ANGD, the loss doesn't move at all during many steps. And at some point, it drops like very sharply. Okay, and in fact, the drop in the loss really corresponds to this phase where the RCE becomes completely flat. Okay. So this was our first observation, and the second one was that, okay, in some cases where we had the variance that was more important between seeds, when we look at the seeds that did not succeed very well, in fact, we saw that instead of having a complete flattening at the end of the optimization, there was a branch that remained unflat. And so because the train loss is at the level of FC0, this was giving like a big difference with the other seeds that completely succeed. It means where the RC became completely flat. And so the other idea we had is, okay, then what happens is if we change the cutoff regularization, and instead of keeping it always at the same level, so here, we put it here where the problem seems to appear, okay? Because in fact, here we already leveraged out all the signal we could. And so the signal that remains to be learned is here. So we change the cutoff so that it's located somehow at the elbow. And then after one natural gradient step, the curve became completely flat. And so this is the first observation. And the second important observation is that, okay, so first we are very happy because we can speed up the algorithm, but also we see that here there is a lot of signal that we did not take into account. And we would like to use it also because we see that, okay, here it seems that we can go up to 10 minus 7 instead of 10 minus, I don't remember, 6 or something. Yeah, 10 minus, no, 10 minus 4. Okay, so here is the square root, so it means that the training loss will be at 10 minus 6 or 10 minus 7. Okay, and so this is the key insights of the new algorithm, what we call the AMStraMGRAM algorithm. And so the idea is really to take advantage of what we show. So we give a precision target that we want to reach. We'll give initial parameters, and we compute the RC and the SVD, and we define those two rank levels. So one is governed by how much. So for how much components the RC is. Sorry, here I did an error. It's under the singular values, and for how much components is the RC above the precision target we wanted. Okay, so we compute that. We apply AnaGRAM with the cutoff rank that is the minimum of both ranks, and we exit the algorithm when we are are above the budget, or when R epsilon is equal to 0. Because in this case, it really means that we completely flatten, and so the train loss it's at the level epsilon. Okay. Okay. And so yeah, the illustration here is there. So here the red is the epsilon level. So at the beginning we are here. At some point we go below the level we expected, and then it's the R epsilon that begins to govern the minimum here, and so we start to flatten the RCE, and at the end it becomes completely flat, and the training loss is at the level epsilon. Okay. Okay, so what are the results? So compared to AnaGRAM, we lower a lot the training loss, but also the L2 error. And so for simple equations like heat and Laplace, we essentially reach the machine precision error. On Galerkin, okay, on some problems which are more high dimensional or non-linear, it's of course we don't have so good performances. And also we compare to Broyden, which is well, at least when we did the algorithm, it was kind of state of the art for pins. And we compare in some benchmark they are better, but we are competitive with Broiden. So for instance, on Burger we are a bit better, and also for the training loss, we are in fact far better, because for instance here we reach 10 minus 24. Okay, so why then? Why? How can we explain the difference? Is that because in our case, when we do the AMStraMGRAM strategy, in fact, we begin to overfit, which was something that, okay, at least I didn't see much papers or even, I mean, it didn't happen for me when I did some tests that an algorithm could overfit for pins. But with AMStraMGRAM, we really have, I mean, overfitting becomes a real problem. And so to illustrate that, here is an AnaGRAM. So here, for instance, we reach a very low residual, which was 10 minus 12. And we see that, so here, so the red dots are the training points or the samples. And we see that in fact, we have overfitting lines. It means that the residual oscillates. And what the algorithm does is to put the part where the oscillation is at 0 exactly on the sampling points. And so then the solution to avoid that is to change the data set, of course. And so here I did another experiment, so another experiments, but adding more points where we had the overfitting. And we see, so if you look at the scale, so the overfitting, it was at 10 minus 3. And here we are, we still have overfitting, but it's at so lower level. Okay. Okay, so to conclude, so the link with green functions. So what is a green function is so the usual definition, or the one that is most common, is that green function is a right inverse. Okay, so what does it mean is that so sorry, the intuition is that you have the source f and you want to use the green function to get a solution. And so what the mathematics behind is that, okay, you define the integral, so the green function is a kernel, you integrate the green function against the source, and so this gives a new function in x, and then when you apply d on this function, you recover f. And this is exactly what you want. You want a function u, so that when you apply d, you recover f. Okay. So in practice, we need a generalization of that, because this is true only when d is surjective. So when d is not surjective, we can define a notion of least-square solution. And then the associated object is the generalized green function, where it's exactly the same object, but instead of recovering the identity here, we recover the projection into the image of D on a space H0. Okay, and so we showed two theorems. Is that in the case where we have an RKHS, then we can explicitly define the green function of the operator by this formula here. Okay, so what is the intuition is, okay, this is, you can understand it as the fact that we define a norm with the operator, or at least so if you compute the scalar product of d, du, and dv, then by computing the adjoints, you will recover this operator. You can define a spectral decomposition on it. And you can then define a regularized inverse of this operator. And then, so the key idea here is that we compute this. We computed this inverse thanks to spectral decomposition on the kernel, and we applied a differential operator on it, and this gives us the green function. Okay, so this is a theoretical result, but the good news is that we can apply it to pins, because in this case, okay, the spectral decomposition is not so complicated. It's just the traditional one of matrices, let's say. And so in fact, we can define this object, which is essentially the same as the NNTK, but here instead of having u theta, we have d of u theta. Okay, and then we show that this function is the green function of the operator on the tangent space. And so in particular, we can rewrite the natural gradient of pins as this update, which explicitly makes appear the green function of the operator. Okay, and so what does it mean? It means that the natural gradient update is somehow optimal as an order one method. Okay, so to conclude, okay, so we defined the empirical natural gradient that gives us an algorithm that scales linearly with a number of parameters. We find a principal way to adapt the cutoff, and this allows us to reach a machine level error on simple problems. We show the connection with the green function, and we have results that are competitive with state-of-the-art optimizers. And we also have lots of perspectives, so we can leverage out the criterion we found, or that comes from the theory, or to find collocation points. Also, so something that is it is already done with FEMS, and it will be it will be out probably at the end of the month. So it's the connection with FEMS. And in fact, we show that we can also define a kernel for FEMS, and that essentially FEMS can be seen as a kernel function. And okay, some open questions. So extend this framework to the data assimilation, so where we also have a data term, and yeah, so extension to momentum, order two methods, operator learning, etc. So these are open questions that are under investigation. Okay, so thank you very much, and we'll be very pleased to answer your questions.
Thank you, Nilo, for the talk, for the great talk. Now we can open the floor for more questions to the speaker.
Can I have a question?
Yes, hello. Hey.
Thanks for your presentation. I have a question about your example for AnaGRAM, for example. Do you have any idea about training time, compare your model and, like, for example, this sporoidin that you have here? You showed us a table.
Yes, here.
Yes.
Okay, I did not compare them on, let's say, well clock time but okay, for this example, so AnaGRAM for AMStraMGRAM, it runs on a single GPU. It runs in a few minutes, I would say 10 minutes, 10, 15 minutes. And SS-Broiden, I think it's comparable. It's, I mean, it's in some cases, SS-Broiden can be faster. In some cases, AMStraMGRAM is faster, depending on the size of the network, etc. But the difference will be by, I mean, it's a constant factor. It's not like orders of magnitude of difference. Knowing that, yeah, this is something also that we that we noticed with Marius, is that SVD is really not. I mean, the implementation of SVD on GPU right now on JAX is really not good. So it's really not efficient. And for instance, if you compare it to Cholesky, there is like constant factor of 100. So like Cholesky runs 100 times faster. And this is purely an implementation issue, because we know from the theoretical point of view that they have exactly the same algorithmic complexity. So there are those things at play also that we
Yeah.
I don't know. I'm not an like a CUDA engineer, so this is something hard for me to handle. But
All right.
Nilo, Elham has a paper which is a follow-up of the paper that you cited by Jorge Urban on optimizing the optimizer. So with the SS BFGS or SS Broiden, we get 10 to the minus 8, actually, for the burgers.
It's very
I
good.
don't know if you've seen that, but we get 2
Ah,
orders
no.
of magnitude better. Yeah. So
Okay.
so Elham will put the it's a published paper
Sure.
in collaboration with Jorge Urban, who is visiting our lab right now. But we improve all the numbers of the initial paper by orders of magnitude. I think Alan Khan is about that or a little better, but certainly the Burgers is 10 to the minus 8.
For
Okay.
AnaGRAM is 10 to minus 7.
7, yeah.
Yeah.
Okay.
I have the
Okay.
archive here.
And that is so it's a paper where you played with the points, or it's a purely a work on the optimizer?
So just optimizers.
Okay.
But there is, I guess, also there's some sort of initialization involved, and I think it's the trust region in different versions of. Elham, you know which one is the best for? Do you remember from the table which one is the best for burgers?
For the burger, the best one was SS-Broiden, and line search was Wolf.
And line search Wolf, yeah, the Wolf conditions, yeah.
And yeah, that we have 10 to minus 8. For
And that's
AnaGRAM,
state of the art compared to, I think, SOAP is around 10 to the minus 6. SOAP from Google.
Ah, okay. Okay.
Yeah.
Okay, so it's.
So we didn't use any weighting of the data or the boundary conditions versus, and I think you didn't use weights here either, right?
No.
Yeah,
No.
exactly. Yeah, that's something that.
Yeah.
But I think in the paper that where they compare the SOAP, they also play with the weights.
Okay.
But,
yes.
yeah.
In fact, this is something also it was a bit hard to compare, because in SS-Broiden they resample the points, and this is something in fact we were more interested into the let's say the pure performance of the optimizer without any other trick. And so yes, we know that there is more comparisons to do with using other tricks and combining them with AMStraMGRAM.
Jorge Urban put a comment on the chat. Maybe Jorge, do you want to speak?
Yeah, well, my camera doesn't work, well, but nevertheless, thank you very much for the very nice presentation. Well, the difference between the follow-up paper by Elham and collaborators and my original paper was that we included other things to refine the results, such as adaptive resampling in the points when you have a bigger residual, which has a noticeable effect, for example, in Galerkin or burgers, where you have a very sharp gradient in the solution. So that's one thing. And I think also the architecture is not the same as the one that I considered in my paper for these two problems, at least. But nevertheless, this type of things like resampling, and because yeah, SS-Broiden, the thing that happens is that if you don't resample the points, you have overfitting. You can check it. So that's why you need to resample the points, and this resampling is important. In particular, yeah, for the example like burgers of Galerkin that you have shown, adaptive resampling is a good way to mitigate overfitting, for example. Yeah.
Okay. Yes, because it's yeah. Also, something I forget to mention is I think compared to your paper, where you enforce the boundary conditions, if I'm not mistaken, or at least the Dirichlet boundary conditions in AMStraMGRAM we had like soft boundary conditions, so it also learns and we saw that this makes a difference also. And
yeah, this could be also, yeah. For example, from my experience, I would say that nowadays initial conditions are always use soft enforcement. But for boundary conditions, I would say that if you impose it via hard enforcement is better. But I would say that this does not has a great effect compared to adaptive resampling and all these kind of things. Yeah.
Okay. Yeah, but this is some things we also, well, I mean, we are planning to test in the next month. But yes, and also here we didn't play really with the architecture. It's pure, I think it's 3-4 layers MLP in general.
The architecture for all comparisons is the same, right? So for AMStraGRAM and SS-Broiden, you use the same architecture or not?
Yes. Unless,
okay,
I mean,
okay.
just the in the case of SS-Broiden, it's with the boundary condition enforcements, while we don't. In fact, we tried to modify your code to have something that is fully comparable, but I don't know. It's there was, I mean, well, I don't remember really, but we were also on a rush for iClear, so I don't know. There was some bug at some point.
Well, also my code works in the optimizer works in a purely SciPy code, Python. So it's if you work with another framework it's complicated to do it in exact way, both algorithms, but yeah, that's okay. For sure, you can optimize your code the same as mine, for example, but nevertheless, the results are pretty interesting. So congratulations for that.
Thank you.
Nilo, is your code available for because we are going through benchmarking all like the natural gradients and SS self-scale methods and SOAP and so on. Is your code available for us to use it to benchmark?
Yes, AnaGRAM is available. I can send you my GitHub. AMStraMGRAM is not yet. I mean, it will be available in next week probably. It's just that we didn't have time to make a clean GitHub repo, but probably next week. Once I'm done with my dissertation, I take some time to do it, and then it will be available.
Okay. Maybe Elham can knock your door and get you involved a little bit, because one of the students of Marius is coming here, and then we'll have a coordinated effort to do a fair benchmarking of all these methods.
Yeah, sure.
So it will be nice to
It's
include your version.
Jimmy, right?
Anas.
Yeah, sure. I will be very pleased. Just maybe wait 1 week because I'm really on the edge of finishing the manuscript.
Yeah, of course.
And
good
once
luck.
it's done, I will have more time.
Thank you, Nilo. Thank you, LM and Jorge, for the discussions. Do we have more questions for the speaker?
I have a question. Hello, I'm Young-Kyu Lee from the postdoc working with George. So thanks for a nice talk. And I have a just simple question for the AMStraMGRAM, because to get the machine accuracy or to prevent some numerical difficulties, you cut off the singular values. But usually when we apply the the Newton type of the method, we usually shift the eigenvalues or singular values using some parameters, or depending on the just compute the largest singular value or smallest singular value and add it. So have you ever tried this one? Because I think because you cut the singular values, you just get rid of some the singular vectors to present the pseudo inverse. That's why it sometimes gives you the overfit or other stuff. I'm not sure.
I don't think the overfitting comes from that, because in the end, when you look, maybe it's not so clear here, but in the new version, so in AMStraMGRAM, we really have like a precision target, and how to say? So we take into account all the signal we need to reach the prescribed precision. So in this case, there is some signal we ignore, but we can just make the assumption that in this case it's noise for us, in the sense that it's something that is not useful to reach the precision we wanted. But so now for the when you do the regression by adding epsilon identity, so we didn't really test it, in the sense that in fact we could not straightforwardly give a meaning to the RC curve in this case, because if you really, to define the RCE, you really use the SVD. So it is not clear what would be the equivalent for a ridge regression. So the fact that you add the identity. But what we did in the paper, nevertheless, is that we gave geometrical interpretation to each of the regularization schemes. And what we show, in a sense, is that you can interpret the ridge regression as instead, or stated differently, when you do the cutoff regularization, you can understand that as modifying the solution space of your problem. While when you do the ridge regression, you don't play with the solution space, but you play with the operator itself. And I didn't include it in my slides because it would have been too long. But if you want, you can go in the paper once we we fixed the compilation problems we have on archive, and we really explain the difference, the geometrical or the functional analysis from the functional analysis perspective, the difference between both, and yes. So I don't know how we could adapt it straightforwardly to the ridge regression, but yeah, it's less clear, let's say.
Yeah.
But probably there is something.
Nilo, if you use adaptive attention weights,
Yes.
I think another thing. I'm sure you will avoid the overfitting, just like you avoided when you do the adaptive resampling. And I think Panos has a question. I don't know if it relates to also some adaptive weights that he has. Panos.
No, it's a different question, but there is a little bit, not very nice presentation, but there is a little bit of magic for the way this thing works. And I'll tell you what is my question. So you said at the beginning that the vanilla pin has an issue because there is an ill conditioning that comes from the differential operator. And then for the natural gradient, when you applied it to pins, you say that you can just apply whatever you had for an usual regression problem, but now you do it for D and B, right? The differential operator and the boundary. So
yes,
that's the magic for me, that somehow something that was ill-conditioned, now you try to do regression on something that is ill-conditioned, and somehow this ill-conditioning disappears. So there has to be an explanation for that. And I don't know if it has to do with the smoothness of your solution that allows you to get away with it. I don't know. I mean, there is something going on there that I don't understand, which you understand, but it's not clear for me why this method works.
Okay.
For the SS-Broiden, for example, I understand because it uses the curvature, so it's able to understand what is happening locally, and somehow remedy this ill conditioning. But how does it work for your method?
Okay. In fact, if you look at the NNTK, yes, here, you can see the inversion of the Gramian here,
right,
as a rescaling.
Okay.
So when you look at when you look at the okay, how to okay, the true, there is two things. There is the numerical interpretation and the theoretical interpretation. So the numerical interpretation is that here, in fact, the Gram matrix really measures the conditioning of your system, and when you invert it, you are precisely killing the conditioning of the system. So the system becomes perfectly conditioned because
right. That I imagine, but there has to be a conservation of trouble somewhere. That if there was an ill conditioning, it should somehow appear in the inverse of this Gram matrix. That somehow that your calculations will have to be sensitive at some point of your workflow. And that's what I don't see. Where this thing is happening and what do you do to avoid it? Because I see the cutoff that you do there when you do the what is it, the SVD of the Jacobian, and somehow something is happening there that allows you to get rid of the ill conditioning. Because just because you say that you want to scale something, it doesn't mean that the actual process of scaling is a well-conditioned operation itself. It could be a difficult one to do and a delicate one to do numerically.
Okay, I don't have a definitive answer to that, but my interpretation is that when we do the AMStraMGRAM, what we have here is here the singular values, you can see them as the conditioning, okay, of your system. And the fact that we cut off, it means that we get back to a simpler problem or a less Hill condition problem, let's say. Okay.
Yeah.
And that's where I think that the cutoff procedure helps, or the adaptive cutoff procedures helps, is that we gradually augment the bad conditioning of the systems up to some point, and then we regress. In fact, what the flattening means that we start by regressing the ill conditioned part, or the most ill conditioned part, and then gradually we get back to better conditioning part. So in fact, we treat it gradually, and so the rescaling is done gradually.
I think this is related to also what Yongkyu was saying, that you do avoid, let's say, the most ill-conditioned part, but you are in danger of throwing out also important information. So you may be regularizing the problem, but actually get solving a modified problem, a slightly modified problem, which is easier. And that's why I was saying that maybe if you have a problem whose solution is relatively smooth, you can get away with it. But if you go to something that is more involved, I don't know if how much you will be able to get away with getting rid of a lot of the singular values there. Anyway, yeah.
That's why we compare it with the RCE, because the RCE tells you how far you are. I mean, here, for instance, we see that with the basis of function we have, and that, okay, this is something I didn't mention, but in some cases it happens that we see, okay, for a problem that has a lot of oscillations, if we take, for instance, one layer neural network, then this RCE remains at 10 minus 1. And this is just because, in fact, in the solution space we take, we cannot solve the problem with high accuracy with the basis we have. And this is because precisely the approximator we use is too smooth. And so if we add layers, then we can have more approximation power. And then we really see that then this RCE becomes lower and lower. And so here, I think that the fact you mentioned that, yes, in some case, we can throw important signal. We precisely control it by comparing it to the RCE, which measures what is the important signal. Because if the RCE is completely zero, it means that, in fact, we are able to completely reconstruct the target on the tangent space.
Right.
And of course, this never happens. But then it also gives you a good insight on how good is your approximator or how unsmooth is your the solution you need, etc. But yes, of course, I mean, it's not a completely magical thing. I mean, it's really bounded by the how good is your the RC.
Okay. All right. Thank you very much.
You're welcome.
Thank
Hello,
you.
hi Nilo. I won't take much of your time. So yeah, just a little question. I was a few days ago. I was going through a paper by Wang and Kiani, and they introduced something called Hessian-based preconditioning for second order methods specifically. So have you
Okay.
came across that for the Hessian preconditioning maybe?
not really. I mean, apart from quasi-Newton methods, not
Okay.
really.
Right. So I had a quick question regarding that how do you think that Fisher information is different from this Hessian-based informations specifically? So yeah, the second question that I noted down is regarding to that. You mentioned that this Galerkin scheme basically is basically we are like through your methods, we are just saying that this is same and performing same as this Galerkin scheme, right?
I mean, performing the same, it depends what you mean. What I am saying with the Galerkin, or do you refer to this or something else with FEMS, or it
Yeah.
was something else? Yeah.
Yeah.
Okay. In fact, what I did is to extend this so this framework to weak solutions, and to show that even in this case, we can see that as a kernel method, and we can apply the same framework, and we can also, in fact, we can show that the FEM or the Galerkin scheme is essentially a natural gradient. Even in the weak formulation.
Sorry, please complete. Sorry. Yeah.
No, I mean, even in the weak formulation, which is not straightforward, we can show that, in fact, Galerkin methods are just a natural gradient method.
Okay. That's all. Thank you.
Okay, you're welcome.
Thank you, Said and Panus, for the questions. Do we have more questions for Nilo?
And sorry, just Said, what was the paper you were referring? Hessian?
Hessian-based preconditioning for second-order derivatives specifically. Second-order method, sorry.
Preconditioning. And this was applied to pins, or it was more
Yeah, it was applied to pins. Yeah.
Okay.
It's a recent paper from Wang and Kiani from 2025.
And Gan, can you write it in the chat?
Yeah, sure.
Sorry.
I can write it. Yeah.
Okay, thank you.
Do we have more questions for Nilo? We can wait until Said has provided the link of the paper on the chat. Yep.
Yeah. Okay, perfect. I copied it. Okay. Okay.
Thank you very much, Nilo. Thanks for the great talk.
Thank you. And thank you for having me.
And good luck with your defense, thesis defense.
Yeah, thank you. And then, I guess we stay in touch. Maybe I send you an email once I'm done, and we can do another Zoom.
Yes, that sounds great. Yeah.
Okay.
Okay, take care.
Thank you. You too.
Thank you.
Okay.
All right. In that case, yep. Thank you. Thank you all for joining this week's session, and thank you, Nilo, again for the great talk. Have a nice weekend.
Thank you. You too.